Okay, 5.2 part 2 is we're going to look more at applications, and then we're going to introduce this new unbounded case. So in the last one we had a theorem, in part 1, 5.2 part 1, we had this theorem where so long as it's bounded, right, it was specific to being bounded, the optimal solution exists and can only be one of the corner points. Alright, so what about unbounded cases? Well, as it turns out, unbounded is harder. And if you really truly to do unbounded cases, you actually need calculus. But we can do one simple example without calculus. Right? So if we look at a unbounded, meaning one side of my graph is open and unbounded, we have one specific situation that we can use the same theorem we had before. Right? That specific situation is, and this is the only situation we'll give you, alright, where I have to have all positive values, alright, so everything has to be positive. So my constraints have to include x values are positive, y values are positive. It's only a minimum case I can find. I cannot find a maximum case. And everything in the minimum case has to be positive. So the x and y values are positive, and so are the numbers in front of the x and y values. Right, that's the only one where I can do the previous theorem. The optimum value will exist and will occur at one of the corner points. Alright, so we're going to do an example of that. Alright, so this first example is going to be that case. So if you'll see, it's a minimum case, so I can only do a minimum case. My x and y values are positive, right, because I included these. And the numbers in front of the x and y values are also positive. Right, and so we're going to find that the feasible region will be unbounded. There will be corner points. The corner points will be on the edge of the bounded side. Right, but one side of it will be open. It will be open on the positive side, so it'll be open to the right. All right, we'll get there when we graph it. All right, so first of all, I have to be positive, so my x-axis and y-axis are boundaries. So remember, my x-axis is the y equals 0, and I want to shade below that. My y-axis is the x equals 0. I want to shade to the left of that. I'm going to save my shading for the end. All right, now I'm going to graph my two functions. So I'm going to start with the first function, which is 2x plus 3y equals 18. And I always graph my intercepts because those typically will be some of my corner points. Alright, so I'm going to start with the y equals 0, so x equals, so y equals 0, that zeroes out. So I get 2x equals 18, x equals, and I did the wrong point, but we'll just switch my zeros. Alright, y equals 0, x equals 9, so 9, 0 is the first point I found. This one, x equals 0, if x is 0, I get 3y equals 18, and so y equals 6. Alright, and then I'm going to go ahead and do my test. 0, 0 is always, maybe I should graph to show you that 0, 0 is where I'm going to test. Alright, we'll do the test after I do my graph. Alright, so I'm going to graph my points. 9, 0, so 9, 0 puts me here. So there's my 9, 0. And 0, 6 puts me there. Alright, then I'm going to try to draw as best as I can between my 2 points. So again, I don't have a straight edge to use with my tablet, but I'm going to do as good as I can, which again is not perfect, but it's the best I'll do. Alright, so my blue line represents 2x plus 3y equals 18. 0, 0 does land to one side, so I'm going to test 0, 0. So if I go back and look at my inequality, it's 0 greater than or equal to 18. So that's false. So I'm going to shade the below it side. So I'm going to shade below that line. I'm going to do my shading at the end. Alright, now I'm going to graph my second line in red. So line 2 is going to be 4x plus 3y equals 24. Again, I'm going to graph my intercept. So this one is x equals 0. I get 3y equals 24. Divide by 3. And so I get 8. So 0, 8 is my first point. And then this one is, I did it backwards again. 8. In my back of my head what I wanted. Alright, let me try this again. Oh, apparently I need more coffee today. X is 0, y 3y. So divided by 3. 24 divided by 3 is 8. Alright, so I had it right. Alright, now y equals 0. So I get 4x equals 24 divided by 4. X equals 6. So 6, 0. Alright, so 0, 8, 6, 0, and I'll test it after I graph it. Alright, so 0, 8 puts me here. That's my 0, 8 point. And then my 6, 0. Alright, so again, trying to graph as straight as I can. Oh my gosh, that one went really wonky. Alright, so that's the line. So hopefully you guys have straight edges. And same thing, I'm going to test 0, 0. When I do test 0, 0, it's going to be less than, right? If I plug 0, 0 into here, it's going to be 0 greater than or equal to 24, which is false. And so I'm going to shade the below it side again. And now I'm going to do my shading. Alright, so everything to the left of the x-axis, below the y-axis gets shaded. And everything below the blue line and everything below, make sure I get it all, below the red line. So everything below all my lines and to the left of all of my lines. Alright. And so there's the false part. And so it's open, right? It's unbounded. That right and above, so to the right of all of those edges and above is unbounded. It goes on forever. And so I'm looking for a minimum. There are corner points. The corner points go through my edges. So remember, this is an edge. And this is an edge. And so I've got a corner point here, which I know what that corner point is. I'm going to call it A. That's the point 0, 8. I've got a corner point where my two lines, C. And I've got a corner point here, which is my 9, 0. And I'm going to call that, I did C first. B, and then I'm going to call this C. B looks to be at 3, 4, but I will need to check to make sure that is actually where my blue line and my red line intersect. Alright, so there's my corner point. So one of those points is going to give me out my minimum. Alright, but I need to verify the B step. Alright, so my corner point A, which was the point 0, 8, which I don't need to check that one because that's one I used. Alright, it went through my y-axis and the point line. 4x plus 3y equals 24, the red line. B was where both my lines intersect, so it went through the red line and the blue line. And it came out, my guess, right now this is a guess, but I do need to check this. Alright, and I'm going to do that in a little bit. C was again one that I used to graph it, so I don't have to check it. It went through the y0 and then the blue line. 2x plus 3y equals 18 and was the point 9, 0. Now, the reason why I said B, if I did a good job graphing, and since mine were a little wonky, I will always check mine. Check and make sure that's actually the spot where the blue line meets the red line. And so to test B, it's going to be I have to solve the system. So either graph it, find where they intersect, or solve the system 4x plus 3y. Keeps erasing. Solve the 4x plus 3y equals 24. The 2x plus 3y equals 18. And you could do that by either doing graphing it, find where they intersect, plug it into your matrix. Is probably what I would do. I'd probably plug it into the matrix. And if you plug it into the matrix, you do find that x equals 3, y equals 4 when you solve the system. So it does check. Another way you could check it is by literally plugging the numbers in. If you take 3 for x, 4 for y, you plug it into the first equation, you should get out 24, and you do. If you plug 3 for x, 4 for y, plug it into the second equation, you should get 18, and you do. So it does check. But you need to check that one because it's not one that I used to graph it. And just in case my lines got a little off, because they could, especially with the way I'm graphing it on my tablet, I should always check the ones that I didn't use the points to graph it. Alright, so now I do what I did before. I take my coordinates, plug them into this equation. So the first one is going to be 0x, so that zeroes out 2 times y, so 2 times 8 will give me 16. Alright, 3 times 3 will give me 9, plus 2 times 4, which will give me 8, so that comes out 17. And y zeroes out, 3 times 9 gives me 27. Alright, so there is my minimum. So the solution is, we get a minimum, C, which is 16. I don't know what it is, but I assume it's cost, when x equals 0 and y equals 8, right? At this point, when x is 0, y is 8, it's the corner point, that gives me out my minimum case, because that's the only case I can have when it's unbounded, right? This is an unbounded case because the solution set is open above and to the right? There's infinitely many, and I can only do a minimum. If it's a minimum and all my values are positive, all my x values and all my number values are positive, then one of the corner points on the edge that's bounded gives me out my minimum. Alright, so that's the other case we'll look at. So next we're going to kind of look at applications, and we'll get both cases. We'll get bounded and unbounded. Now, more common is the bounded cases, but we will do another example of unbounded as well. So we'll practice bound. Basically, from here on out, there's nothing new. We're just going to be practicing applications, solving for max and mins of bounded regions and unbounded regions. Alright, that's what we'll get to in the next videos.